Hi guys, today in our series of understanding databases and how to scale them, we are talking about Postgres architecture. The internal of Postgres will help you understand what it takes to handle the massive read and write workload in your production system. Let's go and deep dive into it. Whenever you try to build a application which is interacting with the database, you need basically a client which can interact with that database. For Postgres, we have various client in various languages: Go, Python, etc. Whatever is your application language, you can choose that client, and through that client your application basically forwards various read and write operations command to Postgres engine. So once your client starts, or once you issue an operation through your client, uh, internally it requests for a connection, so that it can establish its connection with the database which is residing in somewhere in the network. The connection request is like handled by postmaster, which is the main process of this entire Postgres engine. And it is like, although it is responsible for various other activities also, but like you can assume that postmaster is a coordinator, or a main process which is basically managing multiple processes that are running within the Postgres engine. So once you send the connection request, Postmaster sends it to authenticate it with the help of authentication process which is running internally. Authentication process uses LDAP, PAM, etc. Whatever you have configured as your auth server to authenticate that user with the help of username, password, or whatever unique thing you have provided along with your connection URL. Once if your credentials are valid, the request goes to a connection pooler service, which in this case is a PG bouncer. PG bouncer basically is responsible for making sure that it is able to give active or ideal connection, active connection to the request that comes in, and also manages the amount of connection that it can give, or it can easily use for handling these type of requests. So PG bouncer checks that whether the connection is available for new request. If it isn't available, it basically abort those that request. If it's available, it the connection succeeds, and congratulations, your clients get connected to a Postgres engine. Once the client has been connected, a internal backend process start. Basically, the postmaster spawns that internal backend process against that connection, and this backend process is basically responsible for executing the various operations that you want to execute on the DB. So once you spawn this backend process, basically it has a it handles all that operational instruction, whether it's a select instruction or insert instruction or update instruction. Whatever instruction you have passed on to the database is handled by this backend process. Since it's a process, so definitely it has a memory. In case of each backend, we have work memory and temporary memory allocated to that process. You can assume that work memory is basically a memory, as a name suggests, where the actual work that process needs to do for that operation is performed with the help of work memory. And in the Postgres configuration, so we specify that amount of work memory we can give to to each of the backend process. And then there is a temporary buffers and maintenance memory, which for this context let's not discuss about it, but you can assume these are additional buffer spaces which are available to perform various other backend operations, backend process operation, which is needed time now and then. So apart from the backend, the system memory is like entire system memory, apart from the memory which is allocated to each backend process, also has a shared memory. And this shared memory is basically like shared buffers, wall buffers, indexes. So these type of memory requirement for these type of operations is being handled by shared memory. because it is common across all the backend processes and the background processes, hence it is called as a shared memory. Shared memory is generally used by background processes. For example, val writer is one of our backend process which is responsible for writing the sequence of event into the database, into the disk. So for example, if event 1, event 2 happened in the entire Postgres engine, it will record a log of it and store it in a disk. So this is the responsibility of val writer. Similarly, there is a BG background writer or a BG writer which is responsible for putting all the set of records that needs to be inserted into a database onto the data files and these data files are written on the disk. So all the operations that are happening on your data, basically these operations needs to be consolidated and kept into a disk in form of data files, this is being handled by BG writer. So BG writer is basically writing the finalized data records in your disk files. For example, if you issued an insert statement of inserting a row, that row should get inserted and that record should get created on a disk is the responsibility of BG writer. But if you want to make sure that the event of insert had happened on the database, this log has to be created internally, so that in case of failure we can read that log and replay it into the database, so that database emerges into the same state. This is being handled by val writer, and hence the val writer plays an important role to write these logs of event that had happened on the database. Third and most important background process is check pointer. So check pointer, you can assume that check pointer is a coordinating process which is coordinating between val log and BG writers, and checkpoint itself is a time or a point in time where this process has runs and make sure that all the logs which is in val buffer, which we discussed in the part of shared memory, or all the data points which are there in the working memory of background processes are basically flushed into disk with the help of BG writer and val writer. Once it checkpoints that data, or once it makes sure that all the disk all the data, all the dirty writes or dirty copies of that data has been written into disk and been finalized, it basically logs that checkpoint again onto the val log file. So why it is important? Because in case of failure, we can go ahead and read the val log and try to understand that at what point the last checkpointing operation happened, and after that point we can stream entire val log of which is the sequence of event which must have or should have taken on this database. We repeat all those events so that database comes into the same state. So this is the basically a usefulness of check pointer process. So these are background processes which are running inside the Postgres engine and making sure or making use of the shared memory and the background process to perform various such operation on the database. Apart from that, there are other background processes like auto vacuum, which is responsible for cleaning dead files from the disk, and similarly there are archival processes which are running. So these are various type of background processes which basically runs. But for like sake of understanding the Postgres engine internals, these three process plays a very important role in entire making sure that the entire asset property of Postgres is being restored. So these data files are basically then or data files or val log, all these files resides on the disk, and disk may be hard drive or SSD or RAID, and this disk basically stores these files. To understand that how these files or the data files are stored, it is important to understand the way it gets stored into the disk, because it will help you to understand that what causes the slowness in the system or from the disk side. So as you can see that each record or the each list of item which are part of a row is called as a record in the Postgres. So you can say the record is the set of inline variables that needs to be stored in the system. Then there is a concept of pages. There are multiple pages and each page consists the set of records. If these records are the inline like linked list type of database like data structure and storing inline variable one after the other, then you can imagine that there are multiple chunks of such records stored across the pages, and this reflect is directly proportional to the number of like rows or number of data points basically you want to keep in the database. Pages has a defined size, so on that defined size only the entire records or the set of records are being kept. And each record has a specific length which is being also stored, or the pointer to the starting of the record is kept inside the page footer, so that you can easily navigate to any specific record inside a page by just navigating with the help of pointer. And also the length of that record is kept along with that pointer, so that you can skip by that much point in order to reach to next record or the next available adjacent records. So these are basically pages, and then these pages are basically organized in a certain structure, so that we navigating across these pages is easier. In this diagram you can see that there are certain pages which have which are fully written and they don't have any more space to write any new record, and then there are certain empty data pages which is responsible for writing the new data which is coming into the system. And this entire set of records are being stored in the form of heap tree. So basically, as you can see, there is an header page is the page which is currently being written, and then there is a pointer from the header page and towards the header page, so that navigating across pages becomes easier. So basically this is the higher level view of how these data records are being kept inside the disk. And then according to whatever disk we are using, whether it is HDD or SSD, these records are being kept in certain pattern depending on the type of disk we are using. Generally, when we are using HDD, the storage is mostly random, and the seek time to get the record or the read that record from the disk is generally 7 to 8 ms, which is being reduced by SSDs, because then they store the records more linearly and sequentially rather than randomly, and hence SSDs become more faster. So this directly impacts the IO speed, that at the speed at which we can input and output the data from the disk. So this is basically the entire internal structure of the Postgres engine. But this also helps us to answer few of the question. And these are broader thesis of understanding CPU, memory, and disk workload that this entire architecture can incur on our infra, and accordingly we can take various scaling calls according like whenever we see certain types of symptoms. So we will discuss about few symptoms in this video, and but it highly is very contextual to your production use case, and how you are debugging. I will try to give a mindset or a framework in which you can try to look at what is causing the bottleneck in scaling your Postgres database. So CPU workload is, as you can see, that we had a connection pooler which is maintaining the set of connections, so that we can interact with the Postgres system. If your load increases, you have to basically spawn multiple connections, and these connection is directly proportional to the CPU cores that are available. So you have to make sure that you fine tune those connection at a point where you don't incur more cost on CPU or more load on a CPU, and it is proportional to the number of cores that are present in the database instance that you have hosted. Secondly, when your write operations are increasing, the Postgres has an internal locking mechanism to control concurrency issues between multiple writes operation between same set of record. So basically, if there is a row or a record row which has been updated by two processes, it makes sure that if process P1 occurred at time T1 and process P2 occurred at time T2, such that T1 was less than T2, the order of the operations on these record happened in the same order of the process which came earlier compared to the process which came after. So this is basically maintained by the MVCC process which is running inside the Postgres engine, and if you are having more writes, basically this process needs to be scaled so that it can handle more writes and make sure that your integrity and of the system is maintained. Integrity and consistency of the system is basically maintained, and hence this process increase, the number of processes doing this increases, and which can incur your the workload on your CPU. So you have to make sure that that this is being taken care of. And like lastly, with increasing data, your index sizes increases, and index is basically a data structure in which you store the set of navigating pointers so that you can read the record from that disk easily. And these pointers or these structures are can be a B tree type of a structure, can be a hash map type of structure. It depends on type of index that you have created. So as your data size grows, these index also grows, and hence the read and write operation from on these indexes also grows, and hence we generally faces certain type of compute usage when your index size is increasing. So these three broadly can give you a framework of how to see CPU workload while you are working with Postgres engine. Let's talk about memory workload. Memory workload, as we saw, that every backend process has a working memory where it perform various operations on the data files that they are getting or reading from the disk, and then they are manipulating, these processes are manipulating those data points so that it can provide a specific answer to the user query. So when basically the data size increases, the number of pages that are scanned and pulled off into the working memory of of those backend process also may increase, and hence the memory usage of these backend process may increase. And if and in order to handle it, we have to make sure that the number of rows that we are scanning or number of records that we are scanning from the disk and providing it to the backend process are optimal, so that your memory is under control. So with the read workload increasing, this is how your memory per backend process wise increases. Then secondly, again we will talk about indexes, because large index sizes require large amount of storage area, and hence you have to provide larger buffer size, and hence you have to make sure or take care of that as your data size increases, your buffer size is also increased proportionally, so that you can manage your indexes better. And this is somehow a bottleneck of Postgres system, because when you have to power fast read, you have to almost create index for every type of read request, and hence read becomes very difficult to scale on Postgres engine. High read throughput system are generally then less preferable to use, like they are less preferred to use Postgres engine, and better call would be to use certain type of OLAP databases, which we also discussed in our Sentry video. And then the C like third point is on the disk workload. Disk workload is directly proportional to IOPS, and the IOPS are the major bottleneck in case of disk workload. In the 200 GB disk, we generally have 3000 IOPS which are present, and the 3000 IOPS that we can do, and hence the read or when you are writing and reading faster from the disk, apart from the other processes which are relying on the disk are also using the disk IOP, your system tends to become slow, and hence you have to move to a disk or a type of a disk where you can scale IOPS, or you have to keep multiple disk on the network, which is the also one of the fundamental thesis of AWS Aurora, why it was made. So either you scale the disk horizontally or you scale the disk vertically is only the solution to handle the increasing disk workload. So hope this lecture or this entire video helped you to learn Postgres engine internals, and we will continue our discussion again on Postgres, and we'll try to do some hands-on practical on this entire concept of entire Postgres engine, so that you are clear enough of whatever we discussed today in practical terms also.